This is the session 13 from the chapter 3rd. So the main topic here we are discussing is the routing. It's very important. Here will be few problems will be there. So what is the routing means? See in all the cases, either it may be a switch or router, or it needs to be able to look at the destination address and then to determine which of the output ports is nothing but the path, is the best choice to get a packet to that address. Okay. So whether switches will be connected and there may be a many paths will be there. So the choice is which is the best path, which is the best link, so that I can reach the destination. That making a decision to choose a best path is called as a routing. Okay. So here switches and the routers. We have seen switches is for a same kind of internet, internet to the ethernet, LAN to the LAN. So we will use the switches and routers for a internetwork, for a means network to the network. So switches make this decision by consulting a forwarding table, and routers it will construct by a looking at the routing table. And here this route to construct a routing table, we have some routing algorithms, some other kind of algorithms we have. So here we will see those algorithms to construct a routing table and to choose the best link to reach the destination. So before that, before going to the algorithms, we have to understand a network as a graph. Network can be represented as a graph also. So here the alphabets A, B, C, D, E, F, these are maybe either host, or it may be a routers, or it may be a switches, or another network. So from here to here I have to travel. That is the case. So that these are all the connected link. Okay, and this will show you the distance or a cost. From A to F the distance is a 6. We are not bothered about a meter or kilometer, just they have given it as the 6. And from A to E is a 1 and E to F is a 2. So this is a link. So another kind of a graph is also can be represented A, B, C and D. So if there is a direct path is there from one router to the another router, we represent it as a 1 1. From A to B path is there 1. From A to C path is there, we write it as a 1 with respect to the source as a A. But whereas to the D there is a no direct path. So in that case I can also mention in the 0 0. So this one you see in the ADA, in this one we call it as the adjacency matrix, and this one we call it as the cost matrix. Here we take this graph when the distance is not given. I will refer this kind of a graph. When the distance is given, we refer this kind of a graph. So the basic problem of a routing is to find the lowest cost path between any nodes. From A to D, there is A to E is also there, A, B, this is also there, A, F, D, this is also there. Which is the lowest cost path between any nodes, that one we have to calculate and we have to maintain in a routing tables. So routing table, this is a graph. So the two main routing protocols we will be discussing here is the distance vector and the link state algorithm. These two algorithms they give in the problem wise. That one we will see. So in the distance vector we use the protocol routing information protocol, and in the link state we use the open shortest first protocol. So here distance vector, then let that one let's see with an diagram. So distance vector, we'll see here in the graph the cost they have not given, means the distance they have not given, but we have to construct the adjacency matrix based on this graph. So initially distance stored at each node. So here every node will maintain a one kind of a distance node. So initially how it is, from A to A 0, A to B, if the path is there we will write it as a 1, and A to C the path is 1, and A to D there is a distance yet to be calculated, we will write it as a infinity, and from A to E path is there we will write 1, and A to F path is there we will write 1, and A to G still we need to discover, we write it as a infinity. Similarly B to A 1, B to B 0. So this is the initial distance for this network. So wherever the infinity is there, we have to find out the value for a such kind of a nodes. So initial we told every node will be having the this table. So suppose initial routing table at a node A. So initial table at a node A, we will maintain in the 3 columns: destination, cost, and the next hop. From A to B, cost is 1. Next hop is nothing but a via. We suggest it as a via. So A to B directly I can reach, so I write it as a B itself. A to C direct path is there, we write it as a 1 and the C. But whereas the D infinity, E1, F1, G infinity. So at this point A can update its routing table with cost and the next hop. So when we implement the ADA algorithm, how it is calculated now? See, to reach the B, one is there, that is a same. C1 this cost is there, we'll skip that one. But whereas D infinity is there. So to reach D, I have to cover 1 plus 1. 1 plus 1. I can reach via A, B, C, D also, but 1 plus 1 plus 1 it will becomes 3. But whereas where is A to, I have reached already C to D, 1, 1. So the cost will be 2. So the next hop is means via which one we have came? Via C. 1, 1. That's why for a remembering purpose you can remember this as a via. And E direct path is there, F path is there, and G I came here via F, so 1 plus 1 2. Okay, if I come like this, that path may be it will cost much, so I came via F, the cost is F. So this is the updated routing table for a node A. When you implement for this matrix completely here, all the infinity will be replaced like this, the final distance stored at each node. Okay, so this implementation, how it is calculated, there is a in ADA we have a program to find the minimum spanning tree. That program or some shortest path, those program is also there, that can also be implemented here. So here we have seen only the theoretical part, not programmatically we have seen, the theoretical part we have seen. There are few details we need to understand about the distance vector routing. So periodic update of this cost is necessary. Why? Here each node automatically sends an update message often. The frequency of these periodic update varies from a protocol to the protocol. So when it is connected graph to graph, so if it is a connection, the hello kind of a message, like exchange of a substance packet is necessary, and it is done automatically. The second point is The second point is triggered update. Whenever a node notices some link failure or a receive an update from an neighbors that causes it to change one of the routers in its routing table. So notices whenever a neighbor fails, it has to be updated. It's a see whenever a node's routing table changes, it sends an update to its neighbors, which lead to change in their table. So the automatically routing will be updated. When a link or a node fails, the nodes that notice first send network list to distance to their neighbors, and normally the system settle down fairly quickly to a new state. So whenever a link fail, the neighbor will notice first and it will to the further routes that will update this table. So there is a drawbacks of here is also the count to infinity. So to maintain a infinity for a longer time, it may be a waste of time. That is a thing they are telling. Count to infinity. If any link fails, it will be in infinity state till its update. Split horizon drawbacks. The idea is that when a node sends a routing update to its neighbor, it does not send those routes it learned from each neighbor back to their neighbor. Some neighbor may inform, some neighbor may not information. That problem may be there. So this is the distance vector. So where we can implement implementation, I told ADA program, spanning tree, shortest path, cost matrix. That program it can be implemented. And the protocol we mentioned earlier, the protocol we are using here is the routing information protocol, RIP. So what it will do, it will advertise the cost and of reaching other nodes, so the update in table is easy. So small packet format diagram is there in the textbook. You can refer that diagram. So that RIP packet, so it will exchange information to its neighbor telling its cost. Routers running RIP sends their advertisement every 30 seconds. A router also sends an update message whenever an update from another router causes it to change its routing table. Okay. For every 30 seconds, the update is to be necessary. Due to the some drawbacks, it link may fail. Time to leave that may be also lost. So for that purpose, for every 30 seconds, this routing information protocol should be exchanged. And the limitation is also there. It can be implemented for a small network to the maximum of 15 hops, 15 routers. See, okay, this is the RIP small protocol which is used in a distance vector algorithm. So the second main routing protocol is a link state. Link state it uses a protocol open shortest path first protocol. It uses this protocol, and here link state this can be achieved with the two mechanisms. First one is a reliable flooding, and the second one is calculation of the routers. Okay. So the first one we see here it as a reliable flooding. So reliable the flooding, what it means, the idea is it is the process of making sure that all the nodes in a routing protocol get a copy of the link state information from all other nodes. As the term flooding suggests, here a node sends its information to all its directly connected link. This process continues until the information has reached all the nodes in the network. Let's take this as an example. All the nodes will be having the information. Flooding means what? To spread to everywhere. So X, which it will send the information to the A, C and C to the B, A to the B, and B to the D. So D will be having the information of X, A, C, B, means can I reach or there, can I reach it or not. So like that it will be having the information of all the nodes. So by knowing all the nodes, it will construct a small network which can be a minimum spanning tree. So that is as a flood means it will be flood, its information will be flooded to the everywhere. So how this information is flooded means how this that packet is called as a link state packet. Link state packet, that is the flooding packet. I mentioned these will be information will be spreaded everywhere. How the packet name is called as a link state packet. So and actually what this link state packet will contains now, the ID. Okay, the ID of every packet will be having its ID, that ID, and a list of directly connected neighbors and the costs, neighbors and the cost it will be containing. And third one is the a sequence number for a numbering purpose or a accounting purpose, that is a sequence number. Fourth one, time to live, very important, time to live, the lifespan of a packet. So these information will be spreaded to the all the nodes. Okay, when it comes to here X, initially we'll take one of the source X. X will flood these information to here and here also, and C along with the X information to the B, and B along with the A information, C information to the D. When all it is known, we will construct some spanning tree. Okay. There is another technique, calculation of the routers. So root calculation, here we have some calculation purpose. So what this idea means, once a given node has a copy of the LSP, previously we have told link state packet information from every other node, it is able to compute a complete map for that topology or of the network. From this map, it is able to decide the best route for the each destination. I told by the algorithm we can calculate the best path. So that is the we can calculate by the root calculation, and Dijkstra, the shortest path algorithm, is implemented here. So it is how it is work. This is the procedure we'll discuss here. Let's take we'll from where you are starting, from the source I am starting means I will take a in the confirm table I will take I have reached the D with a distance 0 and via nothing, means I am starting here only D 0 and the infinity. So in the second step what I will do, confirmed I will write here, and tentative means from D where I can reach with this path we will mention here. So from the D I can reach the B with a distance of 11, and via which one, via is not there, so directly I will write it as a B itself. See this packet, it may be a source or the destination. Here we write it as a source and here it is a destination. And from D I can reach the C with a distance of 2. Via it is not there, means directly I am connected to the D, so directly write it as the C. Okay, so in the next step, among these which is the shortest one, that one we will put it in the confirm table. So D 0 and C to C. That means I have covered D also and I have covered C also, and still I have not went to the B. I have covered these two also, but in the tentative we try to maintain the same B11 B. Okay, from with the point of a C, we will see the from the C I can reach B now with the distance of C with the D. 2 plus 3 is 5, and via which one? Via C. See, this is the different from other. From C point of view, I can reach B with the distance of 2 plus 3, 5, and the via is C. Okay, so this is the one of the thing. And from C I can also reach the A, okay, with the distance of 10 plus 2, 10 plus 2, 12, and via C. Okay, from the C I can reach B and A. That's the thing. So the next step is continuing. Among these all, which is the common one? That I will cancel it and I will update in the confirm table. So I can reach D 0, C 2, C, C 2, C, and I went to the B5 C. So I went to the B5 C also, and when I reach the B I will skip this part also. Why? Means reaching of B is confirmed here via C. So but A still I have not reached there. I will maintain that in a tentative only, A12 C. Okay, now I have reached B also. From B I can reach the A also. With the distance I can reach the A also via 2 plus 3 plus 5. That will be the 10. So via C I will write here. The first neighbor via C, that one only will maintain here. So that is the path from the B to T is already over. So now among these, which is the shortest? This one is the shortest. I will update here. So D, C, 2, C, then B, 5, C, then A, 10, C. So this is the confirmed graph. So when you construct a confirmed graph with this one, from D, the next we went with the C with a distance of 2, and from C we went to the B, that is 2 plus 3 with a 5, and from B we went to the A with a distance of 5 plus 3 plus 2, which is of 10. So this is the construction of a shortest path. I told you Dijkstra algorithm, it can be implemented here. Okay, and the exchange of this protocol, this information is done with the I told you the packet format is there, OSPF, open shortest path first protocol. Okay, so this is the packet format is also there. That one you can refer the textbook. This is the routing algorithm. This distance vector algorithm, it can be implemented when there is a no cost. It is given when there is a no cost is given, we can implement here to find the adjacency matrix. Whereas the link state, we can use it for a when the cost is given to find the minimum cost. Okay, so these two are important 10 marks question.